right, so our next speaker is a legend. He has a number of really big packages up on CRAN, whether it's Carrot or Tidy models or so much stuff. He's been working on R for what seems like forever. I don't mind tooting his horn too much because he's an awesome guy. He spoke at the first ever NYR, the first ever DCR. He's spoken at many NYRs. He's spoken at the meetup. He's done workshops, both summertime workshops and conference workshops. He's been around forever. But perhaps most importantly, out of all of his accomplishments, this past year, instead of working on a sourdough starter like everybody else, he spent his time perfecting a durian creme brulee. Please welcome Max.
Thanks for coming. My talk is about the pandemic. And unlike everybody who's like, hey, I have the best data analysis for COVID infection rates and things like that, I want to talk about something different, about how I've had this great data set that I've used for training and documentation and testing, and it kind of got borked by the pandemic. In the grand scheme of things, this is the least of anybody's problem. So it's not that big of a deal. Relatively speaking. But for me, I had to figure out a way to mitigate the pandemic issues. So this is what I'm going to talk about. Right, so let's look at the data. So, here's what happened before. We saw basically increasing ridership over time. I think around like 2016, or 2015, it maybe plateaued out. And, 2019 seemed to be dipping down a little bit. So that was a little bit interesting, but not as interesting as now. So, this is pretty much expected. Ridership dropped, and then you see like a slow increase. So, that's now, and this is like really like what I consider to be the data that I'm going to call like the COVID data. So I'll use the phrase like pre-pandemic, which is everything to the left of April 1st. By that dotted line, and everything to the right would be what I'll call the COVID data. And then you can see, on the previous slide, which I'm afraid to go back to, you see these precipitous drops. Those are the holidays and things like that. So, we haven't really gone through that as much here, but I don't think the same data patterns are manifesting in the COVID data as they were in the original data, at least not yet. So that's the situation, and the thought is, well, what can we do about this? I'm thinking about this, like, I feel like, well, this is probably a problem that other people are dealing with. And then David Spahn, who works for me, added me on this tweet, basically every time series data set ever now that we're going to have to live with. So I'm sure this will spawn many, many dissertations and papers. But I thought I'd take a shot at seeing like some ways that we might be able to mitigate the effect of this drop in potential recovery. In fact, this data set I'd rather have because it recovers fairly quickly compared to the trained data. So, I see there's like really two problems here. I mean, the obvious one is that the patterns in the data are completely different. So, how much the previous data, the pre-pandemic data, really is applicable now is kind of in question. Another thing is a little more subtle, and that's a change of scale. So before we were getting like, ridership in like the 15,000s, and now it's like in the low thousands. And so, what we can do is we could try to use different data sets that predict the current data. But if we were to compare a root mean squared error that we get now compared to what we had pre-pandemic, we might still come up with an RMSE of like 2 or 1 or something like that, which seems in the range of what we're getting before, but it's really not the same thing. They're in the same units, but since the scale is so drastically changed, I'm not sure that comparing values we get now to previous years' RMSEs, like pre-pandemic RMSEs, are really applicable. In fact, in the previous year, since the scale was so much larger, some of the residuals that we would get from a fairly good model were bigger than the actual ridership numbers that we're getting now. So they really feel like apples and oranges to go back and forth. So what I'm going to do is I'm going to compare different approaches and evaluate them with different parts of the current COVID data. And since I don't know that we can really compare RMSEs all that well, I'm going to show some visual representations of the fit, especially for the test set. So just to give us, it's more subjective, but it will give us a good sense of like what's going on with the data. So I was saying about how to approach this. Here are the 4 things I came up with. The first one is like, yeah, business as usual. It's machine learning. Let the machine figure it out. And what could go wrong? This is like the antithesis of every feeling I have about machine learning. But it's worth trying out that machines can pick up patterns pretty well, what they do, whether they're really there or not. And then maybe if we just kept going like we did before, it might be smart enough to do the right thing in a predictable way. The other obvious sort of alternative is just use the COVID data. You are kind of starting fresh. We're not seeing the same patterns as we did before, so why use the previous data? And so in this particular case, what I'll do is I'll use the data from April 1st, 2020 and on, and not do really anything different in terms of data analysis. Now, a third approach would be interactions or like a change point analysis. So what I can do is I can look back, and it's actually surprisingly hard to get actual dates from Illinois government websites, but look at particular times where we think there might be a shift in ridership, where, for example, people were first getting vaccinated, or when they start vaccinating kids between 12 and 15 and so on. And so what I can do is I can put indicators in the model for that, and then use interactions with those indicators with the original predictors to potentially be able to model the different sort of phases of the pandemic, at least in terms of like vaccination and things like that. And this, if you were fitting a linear model with these types of terms, it would be like a change point model or a segmented regression model, where you can imagine having like a period of time that is defined by 2 of the indicators, and you would, from the interactions, be able to have like a different slope during those periods. So that might be an approach that would have merit. And then the final thing would be to use case weights. Is let's use all the data, but let's give much, much more weight to the COVID data than the pre-pandemic data. So what I did is I took the pre-pandemic data and gave it like a case weight of 0.1, and then gave the COVID data a case weight of 1, which translates to like each model gives 10-fold more emphasis to the current data than it does to the previous data prior to the pandemic. So those are the 4 approaches I'll use. In terms of the models, what I'm going to do is I'm going to resample them and also hold out the last 2 weeks as a test set. And so in the resampling, I use rolling forecast origin, which is a resampling method that basically takes a chunk of data and then uses the next 2 weeks to make predictions and computes an RMSE on that. So what we'll have is like a rolling RMSE from resampling over the period of the COVID data. So we'll compare sort of apples to apples, looking at these models just at the COVID data in terms of how they perform. Now, there's much more data in the pre-pandemic. So when we look at how many RMSEs we might be comparing, or how many like phases of data we have, there's about 1,000 weeks in the pre-pandemic data and only 25 in the COVID data. And so, you would think there would be much more uncertainty or difficulty in modeling the COVID data because it's much, much smaller. The 2 models I'm going to use are 2 that I know work pretty well for the model, at least pre-pandemic. Cubis is a rule-based ensemble method that's very powerful. Think of it as like XGBoost, but better. That'll stir some Twitter comments up. And that's capable of finding patterns that may or may not exist in the data. It's very powerful and flexible. The other approach I'll use is much more simple, which is a GlimNet linear regression. GlimNet does regularization, so I'll use like a lasso and weight decay penalty to potentially regularize the model. The nice thing about GlimNet is it's less prone to overfitting. So, and it does, again, fairly well with these data. So these 2 approaches are the ones I'm going to take. I'll tune them both about the same amount, and then you'll see in a little bit, I'll use them for prediction to see how different models work. Now, for the interaction approach, what I'm going to do, or for all the models, I'll use the date-based features in the lag 14 features. And then for the interactions in the code there, you see some dates, which, these are rough dates based on what I could find from the government website. Like there's an interaction for when second doses were occurring around January 8th. It was approved for kids around April 10th. And so these are the 6 change points that I could come up with, and then these will be used in terms of interactions. Now, on the first slide, there is a link to a GitHub repo with both the slides and all the code, and a tweet should have gone out about 7 minutes ago that also gives you the repo name. So if you want to look at any of the details of this, please do. So here's the resampling results. So what I have is rows or QBIS, the bottom row is GlimNet, and then the columns are different approaches. So if we look at all using everything, the data is a little bit variable for QBIS. There are some days or some phases, like 2-week periods, where it does well and others where it doesn't. So if you look at each particular dot that's connected on that line, that's an RMSE for a particular 2-week holdout that, again, rolls as over time. And so you can see it starts getting better and better, and then the last 2 is where it goes off the rails. GlimNet does okay, but at least it's stable. So it's slowly decreasing, but the RMSE isn't spectacular. So, you know, all data, not so great. When we look at COVID data only, well, you see a much, much better improvement in both models. They're much more stable, and you know, this seems like a good approach. The interaction model, interestingly, is not all that different in results from the approach where we use all the data. QBIS has the ability to find interactions really easily. So if it would have wanted those interactions, it would have probably used them already. So you don't really see a very different pattern with the interaction approach than the all data. It's a little bit better, but not much. And interesting also is that GlimNet just filtered out, it eliminated from the lasso penalty all the interaction effects. So at least GlimNet didn't think they were that important to model. And I should say I had a little bit of trouble tuning the GlimNet models here. Typically the largest penalty I'll usually use is like 0.1 or 1 in terms of the amount of regularization. And that did really badly. I was getting really bad negative predictions, like off by like thousands of rides, which I'd never seen this data. So I bumped up the amount of regularization and found you know, a good spot where I was getting good performance and reasonable numbers, but the penalties were around 5 or 10, depending on the model. It's somewhat unusual, but not unheard of. And the effect of that regularization is like getting rid of some terms like the interactions that I thought, you know, may have had merit in the model. But clearly, you know, if they had merit, they would have been retained during the feature selection process. And then finally, the case weight approach did well for GlimNet. QBIS, it actually seemed to make things a little bit worse. The instability in performance over time was not great. You know, it had the worst RMSE during a phase. So, you know, that's not great. So it did help GlimNet, didn't really help QBIS all that much. So that's the resampling over time. I think the main takeaway is that from these results is that the COVID data only seems to work well, but for the other approaches, how well something worked or not really depends on what week it is. So it may be too early to tell like how these strategies will work over time. So next, we'll look at the test set data. So here, instead of showing you RMSE values, what I'm going to do is show you the actual 2 weeks of data. And so, so on the y-axis here, we have the actual ridership numbers and their original units, and then you can see the actual fits for QBIS and GlimNet. So we use all data, not great. QBIS does fairly well, except for one data point at the end is really off on a Monday. And then GlimNet seemed to be off like during the week. So for this particular data range, all data, not my best, you know, not my best effort there. For COVID, which seemed to do best in resampling, GlimNet's on it. QBIS like swung and missed. Like during the second week, it's really over predicting the ridership during the week. For the interaction models, again, they're both really not all that spectacular. Again, GlimNet over predicts on the last Monday. GlimNet is over predicting during the week. So, you know, not great. And then the case weights for both models seem to be spot on. So despite QBIS not doing well in the case weights in the previous 2 week holdouts, you know, this is what we get on the current data set, the current last 2 weeks, and it looks pretty great. So that was good. GlimNet's also on the mark here with case weights. So, so, you know, if I had to pick many of these approaches, I think right now I'd take GlimNet for both the COVID-only data or the case weight model. So, our conference, so I, feel obliged to show a little bit of our code. You'll find this in the GitHub repo. Basically, we used unexpectedly tidy models for this. And if we do a group by on the model and the methods and then compute the RMSE and rank them for the test set, what we see is the RMSE we get for the case weights is about 0.5. For COVID data is, about 0.6. And then Cubist case weights comes in at about 0.7. And again, these numbers are much, much, much better than I would have gotten pre-pandemic. But again, even though they're in the same units, the scale is so different that I don't think, a RMSE of like 1.8 or 2 really would have been relevant in this particular case. So conclusions are that the resampling results indicate that really the best strategy is sort of up in the air. Again, the COVID data only seems to be overall the best case, but we don't know how that's going to change from week to week. So it might be too early to tell in terms of making like overall strategy or model assessments. I would say that fitting a high bias model like GlimNet, which doesn't have a lot of room to overinterpret the data, might be the best approach, whether it's GlimNet or something else. So I feel like maybe the current amount of data and the current instability in the COVID data really, for me, sort of makes me think that a model that is a little bit attenuated in terms of the patterns it could pick up would be a good idea. Something that's pretty simple, in other words, would be maybe the best result now. And that's, the regularized linear regression is really appealing because, it slopes and intercepts. It does feature selection. I mean, Cubist does feature selection too, but it's a pretty simple model. I am a little bit concerned about the amount of penalty that was required to fit these models. So maybe over time that'll change, but if I had to pick something now, it'd probably be a linear model on the COVID data only. And then, these are two models. They behave really differently. Maybe some other non-tree-based ensembles besides Cubist would work well. Maybe others wouldn't. And maybe try something like Mars that's in between like machine learning and linear models for these data. Most of the trends are linear in the data set, so something that's linear-ish might be a good choice to pick. So just want to say thanks for the invitation to speak. Thanks to the Tidy Models team, which is Davis, Julia, and Hannah. And Alice Hill has been great on helping us make these excellent looking Sharingan slides. So thanks.
Thank you, Max. I am waiting for you to add GAMs to tidy models. Therefore, you could have your sort of linear experience. So as soon as you add GAMs to tidy models in Parsnip, I think this will all be solved, or at least close enough. And Max is talking, but I can't hear him, but he's backstage talking. I can't hear him. Come back on stage, Max. Oh, sorry, Ken.
They were added in the last release of Parsnip.
Oh, wonderful. I'm behind the times. Thank you, Max, solving my issues before I even asked for it.
And based on Asma's presentation yesterday, last night I added Bart too, but that's still in a PR. So
I saw her. She just tweeted that actually just a little bit ago that you added this. And we just had a number of causal inference talks. I think that's causal. She talked about it, then you went and did it.
Yep.
Or as Dan Chen said, it's a conference-driven development.
That's how we do it, yeah.
Yep. Cool. Thank you so much for everything. And then we had a few people complaining about GlimNet. We don't like the name GlimNet. We want GLMNet forever, right, folks? I said in the chat, my heart sank when Trevor Hasty told me that it was pronounced GlimNet. I'm like, why? I know what. I think it has to do with SAS because they had like proc glim. So I think he was naming it based off of SAS. I'm like, but we're not in SAS. We're in R. Make it GLMNet. But it is GlimNet, sadly. What can you do? So our next speaker